Welcome back, guys. I wanted to hop on because tomorrow we have the Artificial Intelligence Action Summit in Paris. I am fighting a little cold, so bear with me if as I drink some Theraflu here. So why is this important? So there's going to be a lot of big names at this Artificial Intelligence Action Summit, including heads of state, leaders of international organizations, CEOs. And of course, we're on the tail end of all the craziness that happened with DeepSeek. So what is going to happen at this conference? I am definitely paying attention. I'm very interested in what's going to happen. It also looks like JD Vance is going to attend this summit. And I think this is in line with the $500 billion Stargate initiative. As I've said on this channel before, we focus on quantum computers. You can't really talk about the future of AI without talking about quantum computers, because quantum computers are going to be a big part of the future of AI. So that $500 billion Stargate initiative, I think we're going to start seeing some of that money inflow into the quantum computer industry. So let's see. We've got Modi, Macron, U.S. Vice President J.D. Vance as part of the American delegation. We have senior executives from tech giants like Microsoft and Google. And looks like they're going to talk about safety, governance, and innovation. So why does AI matter? How do quantum and AI interplay? Well, I stumbled upon Mindful Machines YouTube video, and oh my goodness, this is one of the best YouTube videos that I've seen that explains quantum AI, Google's quantum AI. And I've picked out some segments for us to watch together. I'll give my reactions, but hats off in advance to Mindful Machines and his incredible storytelling in this video. These are really complicated concepts, and to date, I have not seen a better video that explains both quantum computers and AI and how they work together.
If light is a particle, when we shine it at this double slit, the particle could only go through one or the other slit, and the pattern we would see on the wall would be two areas of light matching the two slits the light is traveling through.
But when we actually do this experiment, we find an interference pattern on the wall.
This is because the light is acting like a wave, traveling through both slits and then interfering with itself. The spots where the amplitudes match are amplified to yield these bright spots, and the spots where the waves cancel each other out yield the alternating dark spots.
Okay, so light is a wave. What does any of this have to do with quantum computing? It has everything to do with quantum computing. And it's not, though, a wave that is. It's at least not all the time. The trouble is we have evidence that light behaves like a particle in other experiments.
Despite the popularity of his theories of relativity, Einstein actually won the Nobel Prize in 1921 for his explanation of the photoelectric effect, showing that light behaves as particles called photons.
The double slit experiment is an anomaly, and it gets weirder.
If we upgrade our equipment here so that we have emitters that very precisely fire single photons paired up with very sensitive light detectors, we still see this same interference pattern. This doesn't make any sense. We are firing single photons one at a time, and over many trials, it still looks like a wave. It's as if each individual particle is somehow going through both slits at once and interfering with itself.
How can a single particle go through two different paths at the same time? That's not even the weirdest part.
If we try to measure which slit the photon actually goes through by adding more detectors just before the slits, the interference pattern disappears completely. The act of observing the photon...
The observer effect is something that's super fascinating when you tie all these concepts together. So when I put together the Quantum Bull Learn page, this was kind of how I bookended all of these concepts. So we have obviously the classical bit versus qubit. We'll go into that in this video. What powers quantum computers, Schrodinger's cat, quantum entanglement, decoherence and interference, and then finally observation as the cornerstone. So the more you study quantum mechanics, the more crazy and incomprehensible it becomes. So how is light behaving in this way? And then as soon as it is observed, it collapses. So that is something that is very, very cool and freaky. Let's use the word freaky. When we're observing a wave, when we're observing any system, it collapses, forcing it to adopt a specific state.
Photons. Each photon has a quantum property that can be measured called spin. It can have either an up or a down spin, but until we measure it, the particles exist in a superposition of both possibilities. Even when they separated the entangled photons by kilometers, as soon as they measured one particle in one lab, its entangled partner in the other lab would instantly respond.
Wait, but
Faster than light, right? He's about to say it.
that would mean that it's somehow communicating with its partner particle faster than light. That's impossible. Nothing can travel faster than light.
Unless space-time is a construct, just another measurable property of a more fundamental quantum field from which all of this reality emerges. Particles only pop out of this quantum foam when a conscious observer makes a measurement.
So, you're telling me nothing is real until we observe it?
More like everything is in all possible states at once until we measure it. And this isn't just philosophical or theoretical, not anymore. As Google proved with their new quantum chip, these weird laws of the universe can be exploited for mind-blowing applications. And the journey from fringe to fortune in this field has been a long one. From about 1940 until as late as the 90s, studies of so-called quantum phenomena were often treated as philosophy at best or crackpottery at worst. Many scientific journals refused to publish papers on these topics.
My brain is hurting.
Okay, so really crazy stuff, and I think he actually does a visualization at some point in this video. It's like a video game almost, right? So when you look up, here it is. So in a video game, an area is rendered, but only the area that you're looking at is rendered. So let's watch this.
Or not. What these physicists proved is that our reality behaves more like a video game, saving resources, only rendering what is actually being observed. They showed this by entangling two particles
Wait. Entangling?
Yeah, so that's another aspect to all of this. This idea of duality. There exist these pairs of particles that are like quantum twins, opposites of each other.
Oh, kind of like you and me.
Wait, is that what you're supposed?
So it's kind of crazy to overlay that onto our reality, that things around us are only collapse into their form when we observe them. But when they are not around us, they're in all possible states at once.
A qubit is like a bit in classical computing, except that its state exists in a superposition of 0 and 1, unlike a classical bit, which has a very definite state. Classical computing relies on these binary bits as the basis of the digital world we live in, where we can encode all of our data as streams of ones and zeros. From this basis, we can derive Boolean logic, which underpins the design of digital circuits and much of computer architecture. With just these simple logic gates, we can build algorithms and circuits that can do any arithmetic operation. But quantum computing throws all of this out the window. You know what?
Let's look at an analogy.
Ooh.
Imagine a classical computing algorithm that can solve a maze. To solve a maze like this, the algorithm has to try every path.
How are you doing this?
Until it finds one that works. A classical computer running this algorithm would basically just check each path and are you even paying attention? Sorry. It's just brute forcing it then. Yeah, like a really fast mouse running through the maze, hitting dead ends and trying over and over and over again. And for simple mazes, this works fine. But as the maze grows bigger and more complicated, the number of possible paths through the maze grows exponentially. That's why, for a particular class of problems, it would take traditional computers longer than the age of the universe to solve. And incidentally, this idea is the basis of cryptography. You know, that thing which keeps your banking passwords safe from prying eyes. Oh. Which, we'll get into that in a bit. So a quantum computer trying to solve this maze would check every solution at the same time in different parallel universes. No, I mean, I would call that explanation incomplete at best. Again, it all comes down to the qubit. When we describe a qubit as existing in a superposition of 0 and 1, we don't mean that it's both values at the same time. If we fall into the trap of describing a qubit in this way, it's easy to land on the idea that a quantum computer achieves its speed by just trying every possible solution in a superposition, that is, at the same time or in parallel. But if this is how it worked, then at the end of the computation process, when we went to measure or observe the state of the qubits, their superpositions would collapse to a random value. In other words, the quantum computer would just spit out nonsensical solutions to whatever problem we gave it. And if that's all you wanted, you could have just picked a random solution yourself. What's actually happening is more subtle. When we say a qubit is in superposition, what we really mean is that it exists in a complex linear combination of states. Complex, not in the sense of complicated, but in the mathematical sense of a real number plus an imaginary number. When we combine these numbers, they create something like a probability wave, a mathematical description of all the possible states our qubit could be in when we measure it. Effectively, this means we can think of a qubit as infinity captured in a box.
That is such a cool quote from this video. And this video is so well done. Like, again, hats off to Mindful Machines breaking this down in such a cool way.
With many different chances of being in many different places. If we come back to the maze example here, the quantum computer would solve it not in parallel, but in a series of discrete steps, which would probabilistically lead to the correct solution. This is because we aren't just running the same binary-based algorithm that a classical computer would run. We need to create specialized algorithms that take advantage of the underlying quantum mechanics. We can create these quantum algorithms using qubit gates. Similar to the binary gates of classical computation, we set these gates up in a deterministic algorithm that causes the superpositions of all the entangled qubits to add together constructively. Just like how the amplitudes of the light wave constructively add together here to amplify the signal while destructively adding together here to leave dark spots.
This is a great breakdown of how this technology. So why I'm showing this is because let's not use the maze as an example. We're talking about reasoning here, right? So take the maze, take the mouse, take the cheese, those metaphors off the table, and replace with the world's most complex problems. Replace that with solving the world's most challenging problems with AI and quantum. So we can see how plugging in AI to quantum has insane synergy, because now we're not talking about a maze anymore. We're talking about the world's biggest problems. And what a crazy milestone it will be in human history when we build a quantum computer that has a capability of answering some of the deepest questions of what humanity is, why we're here, helping us cure diseases and solve climate crises. Just incredible potential.
Now, every time we added more qubits, we got more errors, making it extremely difficult to build useful quantum systems since they were inherently unstable. But this is where Google's breakthrough with Willow changes everything. They found a way to combine multiple physical qubits into one logical qubit. If one cat escapes, the other qubits can correct the error. The more cats you add to each logical qubit, the more stable the system becomes. For the first time in history, adding more qubits actually reduced errors exponentially.
All right, that is a wrap for today. I am looking forward to what comes out of the AI conference. If you have found value in this video, please leave a like or subscribe. I'm a small channel just trying to grow, and have a great day.